All right, so until now, we looked at sort of allocation of private goods, and what I mean by that is that we took each good or each sort of subset of the resource and we gave it to a single agent, right? So that agent takes that subset of the resource, goes home, and that agent is the only agent which can use this resource. Sometimes we also want to think about like public decisions. So here is an example. So let's say we have a set of agents n, we have a set of issues capital T, and for each issue we have several different alternatives to choose from. So you can think of these sort of as issue 1 might be tax policy, so you have several different tax policies. Issue 2 might be immigration policy, you have several different immigration policies, and each agent has a utility for each alternative within each issue. Another example is you might be trying to decide, for example, a family of 3 might be trying to decide what activity they would like to do on Monday, what activity they would like to do on Tuesday, etc. And for each day they have several different options. And again, each agent has a utility for each activity on each day, and we are going to assume that the utilities are additive across issues, right? So for example, if you choose to go with activity 1 on Monday and activity 2 on Tuesday, then agent 1 gets utility 3 plus 5 from that selection. So here note that it's not that we have certain goods that we are going to allocate to agents. We are just going to make some collective decisions which are common to all the agents, and all the agents are going to derive a certain utility from these common public decisions. So first of all, I want to say that this framework generalizes the allocation of private goods. Now at first this may not be very clear. There is this formal description over here, but it's easier to see via an intuitive picture. So consider this allocation of private goods, the kind of goods that we were thinking about until now, on the left here. So you have 3 goods, you have 3 agents, they have different values for the different goods, and you want to partition these goods among the agents. You can frame this as a public decision problem where there is an issue for each good, and the different alternatives for this issue are essentially saying which agent should we give this good to. So this A1 alternative for good G1 issue says that let's give good G1 to agent A1. For that particular alternative, agent A1 is going to derive this utility of 5, the other agents are going to have 0 utility for that alternative, right? So you are only going to have non-negative values on the diagonals, and they are exactly going to represent the values of the different agents for the corresponding goods, and 0 values of diagonal. Okay, so in this way, sort of this framework generalizes the allocation of private goods that we have been thinking about until now. So one question that immediately pops up is what kind of fairness guarantees can we hope to achieve in this public decision framework? Now, one problem is that NV freeness and its relaxations are somewhat nonsensible in this general case, because when you are thinking about NV freeness, you are inevitably thinking about what I am getting versus what you are getting, and whether I would like to get what you are getting instead of what I am getting. Now in public decision space, there is a common allocation that is the same for everyone. So there is no point thinking about what you are getting versus what I am getting, so that sort of becomes nonsensible. But proportionality is still very sensible. You can still expect that each agent should receive an nth factor of the dictatorship utility, which is to say that if they were allowed to choose the best alternative for them from every single issue, they should get at least an nth of that utility, right? So that would be proportionality. Again, it's easy to show that proportionality cannot be satisfied. So one relaxation of proportionality is proportionality up to one issue. This is similar to proportionality up to one good that we saw before, and it says that, well, each agent would have received their proportional share, which is this share here, if they were allowed to change the outcome on one single issue. Right? So you are making a decision on several different issues. You may not be able to give each agent their proportional share, but you are giving something where they would have received their proportional share had they just been able to change the outcome on a single issue. And there is this theorem by Konitzer et al. From 2017, which essentially takes the MNW algorithm, which is still well defined in this public decision space. Essentially, over the space of all possible feasible decisions, you just want to choose the one that maximizes the product of the valuations to the different agents, and that satisfies this prop 1 plus PO. But it's still computationally hard, again, because public decisions generalize private good allocation. Okay. There are sort of other fairness desiderata that people have, that this paper also considers, but we are not going to go into that. Now, there is a setting called allocation of public goods that even further generalizes this public decision making setting with the different issues. So, here is the setting that we considered so far. You have this sort of discrete issues, and for each issue you have several alternatives, and you need to choose exactly one alternative from each issue. Instead of these 6 alternatives as sort of partitioned across the 2 issues, just think of them as 6 different public goods. So think of these public goods as maybe sort of, so good G1 says that we want to build a park somewhere, and we can either implement G1, which means we build the park, and it gives utility 3 to agent 1, utility 2 to agent 2, and 0 to agent 3, or we don't select G1, which means we don't build the park. Good G2 might be a good that says whether we build a road at a certain place or we don't build it, right? And since these agents have non-negative utilities for these different public goods, ideally you just want to implement all the public goods, right? You just want to give positive utility to all the agents as much as possible. So certainly this is only interesting if there are some constraints on which subsets of public goods you can simultaneously implement, right? These can be constraints because of some sort of some budget, or these can be constraints like we get here. So for example, in this transformation, we would say that you in any decision you have to choose exactly one of G1, G2, G3 and exactly one of G4, G5, G6. So this, for those of you who might know a bit about matroid theory, this is essentially a partition matroid constraint, and so sort of this public decision setting with issues generalizes to this allocation of public goods with a matroid constraint on which subsets of public goods you can simultaneously implement. And so in this setting, you want to get a guarantee that is slightly stronger than proportionality up to one good. So first let me define what this delta alpha core guarantee is. So an allocation of public goods, which is simply a subset of the public goods that you can simultaneously implement, is called to be in delta alpha core if for every subset of the agents S, there is no feasible allocation of public goods C prime that they could propose, such that if you take their utility under C prime and if you scale it down by by a factor which is proportional to the size of the group, because certainly we don't want a very small group to be able to propose some alternative decision and then let them sort of have a valid contest. So we are going to scale down the utility by a factor that is proportional to the size of the group. But after doing that, they shouldn't get at least as much as the utility that they are currently getting, times 1 plus delta plus alpha. So if delta and alpha are both 0, then this is very much like a generalization. In fact, it is a generalization of proportionality. It's just called the core. And delta alpha core is an approximation of the core guarantee. And specifically when delta is 0, so there is no multiplicative approximation, but alpha is 1, the score guarantee generalizes a guarantee that's very similar to proportionality up to one issue. But I won't go into the details of that. So there's this Fein et al. Paper that looks at this allocation of public goods under different types of constraints on which goods you can simultaneously implement. So I already mentioned that if you look at partition matroid constraints, then you can recover the public decision setting with the issues framework. You can also look at other types of matroids, and by that this can also generalize multi-winner voting, where you have a set of m candidates and you want to select a committee of k candidates. And for that, they show that 0,2 core allocation always exists. And if you have any constant epsilon that you are willing to sacrifice, then you can actually compute a 0,2 plus epsilon core allocation in polynomial time. And they show that, interestingly, this you cannot achieve by just simply maximizing Nash welfare. In fact, if you maximize Nash welfare, then they show that the approximation that you get here is pretty bad. So remember that it gets sort of up to one approximation of proportionality, but it does not get any good approximation of the more general core guarantee. Instead, what you do is you maximize a smooth Nash welfare which does not react to zero utilities as violently as the Nash welfare reacts to. And they also show that for any epsilon, essentially you cannot get better than a 0,1 core allocation, but whether there always exists a 0,1 core allocation and whether you can compute it in polynomial time are open problems here. Yes?
Does allocation thought includes generalized MultiWinner voting in ordinal setting?
Not in ordinal setting, only in the cardinal setting. So this is all with additive valuation still. So we are still going to assume that if you have a subset of the goods selected, so for example, if these are the 6 candidates, and you can select any 3 of these 6 candidates, then we are still going to assume that the utility to agent 1 when G1, G2 and G3 are selected simultaneously is 3 plus 1 plus 0. So this is still for cardinal valuations, but yeah, it's an interesting question. Cardinal and additive, yes. So that is for matroid constraints. They also have some results for matching constraints where the public goods are edges of a graph, and you can select a subset of the public goods if they form a matching. And for that, they have this sort of delta comma 8 plus 6 by delta core guarantee. So now there's a trade-off between the multiplicative factor and the additive factor. And again, this they achieve by maximizing a slightly different smooth Nash welfare. Instead of just adding a 1, they also add a 4 plus 4 by delta. And again, they show that you cannot get essentially better than a 0,1 core allocation, even if you are willing to sacrifice a lot multiplicatively. And so this problem is still open for matching constraints, whether you can always get a 0,1 core allocation. And they have a slightly worse guarantee which has a logarithmically large alpha rather than a constant alpha in the case of packing constraints. Okay, so that's the end of this part of the tutorial as well. Again, the papers that we referenced in this later part of the tutorial are all mentioned here, and we are going to upload the slides online. So if you are interested in any of these papers, you can look them up. So if that's the end of the tutorial. If you have any questions, then we would be happy to address them now. If not, then thank you all for coming to this tutorial, and we hope that you all at least got to see a few results that you did not know about and a few open problems that you might be excited to work on. Okay, thank you all.